All right, so what we did seemed to work pretty well. So is this a general strategy? Is this a good idea to fix a function space and pick a bunch of functions, try them out, pick whichever one minimizes loss? So that is a strategy, and it is a strategy that's used sometimes. And actually, the particular incarnation of that strategy that we use is something called grid search. So we have this interval here over our parameter c. We check from -3 to 3. We divvy that up into a bunch of points. And actually, in this example, we space the points between, so let's see, c's 1 minus c's 0. We sampled in that range, and they were spaced at an interval of, about 0.01, 0.006 between each sample and c. So that was our resolution. And we could have gone finer. We could have tried even more points. We could have tried 10,000, and then, But yeah, choosing some appropriate number of points to search through, appropriate number of functions to sample, and then we pick the best one. So that's called grid search. But it does have some drawbacks. And really, it's when the space of functions is too big in some sense. When we have too many functions to consider, we're going to have to search through too many things. So even if I just go up a dimension and I consider a grid over some function that has two parameters, not just one, like here we had the c, which is shifting this thing, left and right. But we could have two parameters. You can imagine a two-dimensional version of this sort of thing, where I had points in the Cartesian plane, and I was trying to divvy off some region where I was greater than some x or less than some y, right? And so there I might have two parameters. And so let's say that one of the parameters was x. It was in an interval ranging from -a to a, and another parameter y was in an interval ranging from -b to b. So for a spacing d, so that would be like this, the 0.006 here. So for particular spacing d, that means that we have 2a over d samples that we would take if we were uniformly spacing these for our x, and then we would have 2b over d samples for our y. But remember, we're actually choosing these on a grid. So this would actually be a two-dimensional grid. So we actually have that number. We go up a dimension. We have that number m times that number n. It's really like you can think of a two-dimensional array with m rows and n columns. And each element in that array is one function from our family of functions. And this actually is a number, so it'd be 2a times 2b over d squared. As I make d smaller, right, so I increase the resolution, this grows very quickly. So this is actually going to kind of explode already. And it just gets worse as we go up in dimension. So in general, grid search has a complexity that's proportional to big O of some constant to the d power for a d-dimensional function space. So if I have d degrees of freedom in my space of functions. And so this is really bad. We call this the curse. This is called the curse of dimensionality. So the more parameters that we have in our model, the worse this is going to be. And just to give you an idea of how bad this can be, some of the neural networks that we're going to look at have like 1 million parameters or more. Okay, so some constant to the millionth power, that's bad news. That's probably going to be way more than there are particles in the universe. Okay, so we can't do grid search in general if we're just going to try a bunch, sampling a bunch of different functions uniformly. So we're going to have to get a little more creative. And so let me show you another family of functions that we can draw from, but we're going to be optimized. We're going to be able to optimize in a different way. So not necessarily by searching exhaustively in this grid, but maybe a different way using calculus, actually. Much like you would have done back in Math 111 to find the minima or maxima of functions, right? So we'll figure out a way to do that. And so let's first talk about the logistic perceptron.